Have a good this weekend.
Did you all have a good 3-day weekend?
Yes.
What's better than a 3-day weekend?
4 days.
4-day weekend. There you go. Good. I do have your exams, but I'm not going to pass them out now because then I won't get your attention for who knows how long. We will get those to you. So interrupt me with at least 5 minutes left, because you know how I get going. So just say, hey, time to pass this, and so the last 5 minutes, I'll get you all back your exams. You all did well. You showed evidence of following along. What we will do, let's see, let me open this one up. There we go. Oh, there it is. Okay, good. So I have set up the sort of schedule for the next unit, which is going to be, we're starting with probability today. There was a number of you that need to make up the test. We'll do that on Thursday. And then what we'll do on Friday is I'll make it open for what I call test corrections or test review. So I'll have a little form where you put your question number, what you put, why it was wrong, why you now know the right answer, and then you'll give me the right answer. Okay, and then for that you'll get half the points back. So what it does is it turns a B, so you got 80%, that gets you to 90%. You had 50%, still gets you to 75, so you're still passing. The other option I do, if it works out better for you, is if you learn by the end, the final exam will be cumulative to include everything. So if you do better on the final exam than you did on one of the other 3 exams, I will take the test score from that final exam and replace your lowest exam. Okay, so you can have one bad day and it's not going to throw you off. You'll be able to recover, and again, it's just kind of keep on learning and keep going forward. We're getting into some different content. So today, how many of you know how to count? Hopefully all of you. Yeah, 1, 2, 3, 4, 5. How many of you know how to divide? 4 divided by 2 is 2. Okay, good. That's all you need to know for this next set. However, knowing what to count, that's the little tricky part sometimes. But that's what we're getting into today with probability. And again, this is, I'll go back here. So we've got it set up. We've done chapter 1 and chapter 2. We're starting the exam content for exam 2. We've got your pacing schedule here if you want to check. And basically, once we've covered something in class, you should be able to start into that homework, and the goal will be to kind of finish those homeworks up over that weekend, so that by the next week we're ready to start into the newer stuff. And I've got so chapter 3 is here. It's got the dates. So basically this week I've got our slide deck for 3.1. We'll get that set up. And I think, yeah, I should have everything ready to go. Okay, so basic probability. When I say the word probability, what does that make you think of? Chance, probably. Right, exactly where it came from, probably. It might happen or might not. Okay, good. That's what we're going to talk about. And so the way we make up a measurement system for something happening, it either is certainly going to happen, so we call that 100% probability, or it's impossible for it to happen, we call that a 0%. And then everything else is somewhere in between. And if it's more likely to occur, it's going to be closer to the 100%. If it's less likely to occur, it'll be closer to the 0%. And we're going to look at 3 different measurements of probability today, 3 different ways to measure probability. And that's all this says is, it's going to be between 0 and 1. It either doesn't happen or can't happen. Say like rolling a die and getting a 7. There's only 1 through 6, right? You can't get a 7 if you roll the die, unless you got a cheating die. But with 1 die, you can't get it, so that's impossible. And if you had a die with all 3s on it, it'd be a 100% chance of getting a 3, right? Because they're all 3s. That's all that's going to happen. So that's what happens. Closer to 1, the more likely it is. Closer to 0, the less likely it is. And we're going to see there's some mathematical ways to do that that involve counting and division. And there's a couple others. Okay, so we're going to talk about probability experiments. It's a little different than what we were talking about than when we were talking statistical experiments. But a probability experiment is a professor sitting and rolling a bunch of die, or flipping a coin many times. That's what a probability experiment is, to see if in the real world what happens, what we think is going to happen. Okay, so we've got a theory behind things. Flip a coin, 50-50, right? Well, you flip it a bunch of times, we see if that actually happens. So probability experiment. Each probability experiment has an outcome, and that's the thing. What's an outcome? It's what happens with a single trial. So you flip a coin once, and you get an outcome. Okay, you roll a die one, you get an outcome. So this is just kind of vocabulary, so when we start talking about it, we all are on the same page. Sample space. Now, this is a little different than what we were talking about sampling from a population. This case, the sample space is actually the population. It's every single thing that can happen. So it's a set of everything that could happen. So you see how people who did probability probably didn't talk to the people who did statistics, because now they're using kind of sample in two different ways, right? This is really talking about the population of anything, of all the things that could happen. And then the event is the one thing or a couple things that we're looking to have happen. And probability is just about counting how many things are in that sample space, what are all the things that could happen, and then count how many things are in that event that we want to happen, or don't want to happen, but that we're looking for, and we divide the two, and that's a probability. Simple, right? Hopefully. But it's, again, it's the wording of some of the questions that can get tricky, and we'll go through those. So, first of all, we got to learn how to count. Again, we think we know how to count, but there's some quicker ways to count. What is addition, really? I've got 3 in this hand, 4 in this hand. 3 plus 4 is 7. It's really a faster way to count instead of counting them individually, right? Multiplication. 3 times 4 is really 3 plus 3 plus 3 plus 3. It's a faster way of counting. So we're going to see how both addition and multiplication really are ways of counting. Okay. So we want to look at something. We've got this big word, fundamental counting principle. What it tells us is if you can do something multiple ways, a series of successive things can occur. We can count those by using the multiplication principle. So I see you all were able to get dressed this morning, and when you got dressed you had some choices, right? So what if you had available 2 pairs of jeans, 2 different jeans, 3 different t-shirts that you could wear, and 2 pairs of sneakers to choose from? How many different outfits could you have chosen? Would it make sense that you choose between the 2 jeans, depending upon which one you got, the 3 shirts, and the 2 sneakers, give us 12. Now, does that make sense? Well, we're going to use a tree diagram to kind of visualize this. Here's some guy getting dressed. He's got the blue jeans or the black jeans. Chooses one of them, depending upon which he chooses. Then he's got 3 different shirts to pair from. So now we've got 6 different outfits without any shoes on yet. But then he's got black sneakers and red sneakers. And so if you count them, yes, there's 12 different looks he could have had. Okay, and that's that multiplication principle. Okay, we get to use this again and again, but the tree diagram works kind of nicely to see that, yeah, that seems to be what's happening, because even if something is sort of common sense or seems to make sense, we still have to test it out mathematically. Okay, so far so good? So if you got multiple things you can do, just multiply it, right? Step by step. See, some of you are in medical, looking in the medical field. Blood types, right? How many blood types are there? 4 different blood types, O, A, B, and AB. How many of you know your blood type? I always forget though. I think I'm A, but I might be B, and that's a big difference, right? So I have to go to the donation, and then they'll tell me. But then including your blood type, you're either positive or negative, right? Rh positive, Rh negative. So how many different blood samples with type and positive or negative could we get? Would it make sense, since we've got 4 here, there's a positive or a negative, you can't be both, you're one or the other. How many would that give us? 8. Very good. And again, we could use that tree diagram to kind of plot it out to make sure, visually it's, okay, 4 of these, each one has 2. Yeah, we're going to get 8 different options. And that becomes what we call our sample space. If we were doing some probability, what's the probability randomly choosing somebody and they had an A-. Now this was if they were all equally distributed in the population, but some types are more rare than others, right? One of them is the universal donor. Does anyone know? O negative, okay. Cool. And that's, so you means you can give your blood to anybody. That's cool. And there was one, I think, the universal recipient. Which one? AB, you can get blood from anybody. That's kind of cool. So, you guys know a lot more about that than I do. But anyway, my mom was a nurse, but I couldn't help her with her homework because she tried to get me to help her, but I couldn't. Okay. So, then the other thing we want to talk about is events. There's what we call a simple event, which means it has only one outcome. So if we talk about a simple event, and so here's an experiment. Someone's going to flip a coin and then roll a dice. A die. Die is single, right? So what's the probability of tossing a heads and rolling a 3? Well, tossing a heads is here, rolling a 3 is here, and notice there's only one of all the sample space that happens is, so if there's only one event, then we call that a simple event. What would a non-simple event be?
There's more than one.
There's more than one. Okay, so again, just so when we talk about things, so if it was tossing a heads and rolling an even number, okay, get rid of this, tossing a heads, and then an even number, we see there's 3 different options, right? 3 possible outcomes that fit that. So that's not a simple one. Okay, simple or not simple. So far, so good. Not too bad. Okay, we're going to ask you just to identify this one. So we've got quality assurance. You randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. Is that a simple event or a not simple event? Simple because why? The event is getting a specific, which is an individual machine part. So not any machine part or something. So yeah, so that would be a simple event. Only one that you get that one machine part. Okay. How about you roll a die and the event is rolling at least a 4?
Non-simple.
Simple, why?
Because that says at least a 4, so you could roll 1, 2, 4 and still be good.
At least 4 means what?
Like you can roll 1, 2, 4.
4 or bigger.
4, oh, I'm sorry.
4, 5, or 6. But you had the right concept down. This is what we were talking about. Yeah. So, and you demonstrated what I mean is a lot of times it's these one words, and sometimes we think of it the other way around. So at least 4 means 4, 5, or 6. But it's easy when we read these things to think of it's 1 through 4. So there's a few words we're going to get to like this: at least, at most, at. We got to figure out, does that mean equal to or greater or less than, and all those kind of words. Okay. But so far, concept is simple, one outcome. The event has one outcome. Not simple, more than one. Good. Now we're going to look at the kind of formalize this. This is with the guy getting dressed. He had 3 different things, right? And each one we're choosing from. So that's all this is saying. If you have M different ways of something happening, and a second thing has N different ways, if you multiply them, you'll be able to count all the different ways that can happen. Okay, so we had two jeans, 3 t-shirts, and 2 shoes, 2 times 3 times 2. So let's take a look at this. We're gonna buy a car today. And we have 3 different manufacturers to choose from, 2 different sizes, and 4 different colors. How many different combinations of all these could we have choose?
24, right?
3 times 2 times 4, so yeah, 8 times 2,
24.
24. However you want to
I
multiply.
literally had it down. Because you said so, and I was confused.
Yeah, so we have to multiply all together. And again, we can use this concept of the tree diagram to kind of visually see it, but you kind of see like this, doesn't it start to get messy? You get, yeah, because you got 24 things down here, but it's just each time, each step of the process, as you're choosing something, you're just multiplying how many times each one has. Okay, and so I wouldn't make a tree diagram necessarily, especially if there's a lot of things going on, because you'll just be so messy. But if you think about it, and branching out, branching, then it helps make it more sense. Okay, so now we're going to get into some more abstract ones, but it's the same process. So we've got an access code for the car we just bought, has a security code, and it has 4 digits. Each digit can be a number from 0 to 9. Now how many digits is that, 0 to 9? Is it 10 or is it 9?
10, because you're counting 0.
Because you're counting 0. What I encourage you to do is count with your hands, because your fingers don't lie. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it's 10. Because I make that same mistake. 0 to 9. Oh, that's 9. No. 1 to 9 is 9, but 0, because of the 0, that's actually 10 things. So again, counting can be simple, but it's also simple to forget one or put an extra. So there's 10 different digits we could put there. So let's go through a couple different options. So the first one is each digit can be used only once and not repeated. So here's our 4-digit code. This is kind of a nice way to do all these types of problems. Is however many choices we have, what I do is I make a little slot or a little box. So for our first, and we think, my first digit, how many choices do I have for that first digit? 10, 0 through 9. So I'm going to put my 10 here. But now that I chose a number, and I can't use that number again, how many do I have for the second slot? I've only got 9 left because I've used up one of my choices and I can't reuse it. And I'm just going to put a multiply here. Okay, I choose one. Now what's left? 8. And then there's 7 for the 4th. We're going to come back to this. We'll do a little more formal counting, and you'll see there's a whole mathematical process that's called factorials that kind of takes this thing. But 10 times 9 times 8 times 7. Could somebody help me out with the calculator on that one?
Would you use 10? Because since it's only started, since it ends at 9.
0 to 9, right? There's 10 different digits. We could put a 0 at the front
Okay.
in this code. So this one doesn't, but keep that in mind that we could use 0 on this first one. So we have 10. What did you end up with?
5,040.
5,040. Okay, good. Now let's see, the second one is each digit can be repeated. So in this code we can repeat them. So let's go with that. Here's number, so this was number 1. For number 2, how many do we have for the first one? We could use 10, any of the digits. Since we can repeat them, we still have 10 because we can reuse them. And we still have 10, oops, that looks like a plus, it's a multiply, and 10. So 10 times 10 times 10 times 6 because we can repeat. Which gives us 10 to the 4th, which is 1 with 4 zeros, and that's 10,000. Very good. Almost twice as much, not quite, but almost twice as many because we can repeat. See how that works? Okay, so, and again, when you're doing these types of problems, so we get the probability, you have to watch for that. What are they, the words, what are they saying, what we can do and what we can't do. Can we repeat? We're gonna get different than if we can't. And the last one, each digit can be repeated, but the first digit cannot be 0 or 1. So now, since the first digit has some restrictions, how many choices do we have for that first digit? We've only got 8. We can't use 0 or 1, so that leaves us with 8 here. But we get to the second digit, it has no restrictions. Back to 10, right? Because we could use any 0 through 9. And we can even repeat whatever we use. There's not, it didn't say, well, yeah, it did. It said you could be repeated. And then we've got 10, and then we've got 10. And again, we multiply these, 10 times 10 times 10, that's going to be 1,000. 1,000 times 8, 8,000. So notice just putting that little restriction on the first digit that you can't use those two, we're down to 8,000 possibilities rather than 10. Which one's more going to be maybe more of a secure code? The one that there's more choices, right? 10,000, you can't. You think if you're going to randomly guess that code, if you had 10,000 different possibilities, it's going to be harder.
Why is it 8 on the first digit again?
Because they cannot be 0 or 1. So you can only get 2, 3, 4, 5, 6, 7, 8, 9. So that's why I like my fingers don't, yeah, I can see it. And otherwise it's all abstract. So I encourage you to find whatever method, that's why we use the tree diagrams if you can visualize, but it's okay to use fingers. Actually, remember from the early part, fingers are where math comes from, how we looked at the fingers. Yes?
Why is 10 the max number?
Because that's all we have is 0 to 9. That's the only symbols, so there's only 10 symbols we can put there.
So then 10 would basically just mean 0. Like it would represent the number 0.
Right, you could think of it that way, and that's called a modulus system. Yes? You use 8 because there's only 8 symbols you could put there. So we can't use 0 or 1, so we can only use 2, 3, 4, 5, 6, 7, 8, 9. So there's 8 things we could use, yeah. Because of that restriction. Now the other ones didn't have a restriction. If they put an additional one on the back and said, oh, you can use 8 or 9 on the back or something, you would take those out. So one of the things you may be finding out when we're using digits, 0 through 9, and then we're but see these digits here are the count of how many we can use, which is different than the numbers themselves, right? And that can get confusing when we're counting. So there's a lot of different things that come up, but hopefully you can see the difference between when we're using digits as a symbol and then when we're using the count of how many we had. And it's, yeah, if we had like, how many of you, any of you do programming or computer science? No? They got something called hexadecimal, which is actually, I think 16 digits, right? Because they do everything 2 to the power. So they've actually got, if you use the hexadecimal system, you have 0 through 9, and then they include A, B, C, D, E, F. I think to get 16, I'm not even sure, but I don't use it enough, but there's 16 different symbols you could use. Okay, so there are different base systems, but we won't get into that. Happy about that? Yeah. We'll stick with the 10 numbers. Okay, so far so good? And you're going to stop me when?
5 minutes.
Thank you, because you know me, time. Okay, so that was all the part of how we count. And once we count, we divide. What do we divide? We counted the number of outcomes in the event. And remind me, if it's a simple event, how many outcomes will there be? Good. Well, that's the easy one. If it's not simple, then there may be more than one. And then we also counted in fact, actually, that's what we were using the multiplication is to count how much is in the sample space, how much is in really the population of everything that could happen. Could you ever have more events than you have in the sample space. Would that ever be possible? Unless you made a mistake, right? That's the only way it'd be possible. Because the population's everything, how can you have more than that? If you had more than that, then you forgot to count something. So I guess, you know, it's possible, but if you ever get above 1 or 100% in a probability problem, you forgot to count something. Okay? This will always give us a number somewhere between 0 and 1, or if you want to think of it, 0% and 100%. Okay, so our probability of anything happening is always got to be between 0 and 1. Could be 0, could be 1. And we'll see that again. Make sense? And again, it's just, that's what the sort of the measurement, the rubric they chose. If it's not certain to happen, that's 100%. It's impossible to happen, that's 0. And it's going to be somewhere in between. And it's just a simple count, both the events, sample space, and then divide. That's all probability is. But we're going to see we got advanced probability, so the way, what we're counting is the difficult part. What we count. So let's just do a few quick examples. You have a 6-sided die, probability of each. We want to roll a 3. What would that probability be? Well, how many 3s are on a 6-sided die?
1.
There's 1. How many different numbers could come up? 6, 1 through 6. And so there's our probability, 1/6. We could write it that way. You could take a calculator and divide it, and you'll get 0.167 rounded, because 666 repeating. Or you could also write it as a percentage, 16.7%. So there's 3 different ways of writing a probability, either as a fraction, a decimal, or percentage. I like percentages because it's just easier on my mind. Think, oh, that's about 17%. Okay, but whatever you prefer. How about the event of rolling a 7?
Same.
Careful.
Oh,
It
wait.
got me
Yeah.
too. Okay. How many 7s are on the die? There's none. Okay, so we do the counting as well. There's 0 7s on the die out of 6, which gives us a probability of 0. That's an impossibility. You cannot roll a 7 because there's not one on there. Okay. You need 2 die to do that, right? And then event C, rolling a number less than 5.
There's
4 numbers, 1, 2, 3, 4, 1, 2, 3, 4, that are less than 5. So that's 4 out of 6, which reduces to 2/3, which is 0.6666 repeating, or 67, which you could write as 67% rounded, right? Make sense? Count and divide, count and divide. It's probability. And what you're going to see is we're taking this probability, we'll do 2 chapters of it, and then in the last chapter we start tying it back to statistics, how it's used in statistics specifically. Because that's part of what we're doing with statistics is we're counting things, but then to predict, to get that inferential statistics to predict, we need the probabilities to say all that stuff, okay? So yeah, here's our sample space, 1 through 6, and we got these numbers. So far making sense? Okay. Now we get into what we've been doing has been called classical probability. I like to call it theoretical probability. It has the understanding that when you have a die, each side is equally likely. Have you ever heard of something called loaded dice? You put a little bit of weight on one side, so it's more likely to come up a particular number. That's not what we're talking about in probability. It has to be fair die, which means it's equally likely. A coin, you know, one side's not completely heavier than the other. So this has the concept of equally likely. Classical probability. Now there's another type of probability, and this often, well, not often, this is a type of probability we use in sports. And it's what we do, because you can't say, measure you mathematically and say you're a 40% hitter. You know, you get up, you're gonna get a hit 40% of the time, right? Batting average. What do they do with batting average? They observe each person hitting, and the number of times they get a hit, that's the event, divided by the number of times they get up to bat. The total things that were observed. When you strike out, you still got up to bat, but you didn't get a hit. Okay, and so then that gives you empirical probabilities. And notice the number down here, the total of things happening, is your frequency of everything that happened. In the top, it's just the frequency of a particular event. Baseball or softball, the event is you got a hit. Okay. So that's how you get a batting average. If you're a pitcher, I don't got any pitchers here. They have other statistics, but they measure it, yeah. So they're just observing how many times. If you're in basketball, how many free throw percentage are you? Every time you shoot a basket, did you make it or did you not? Times you did go in the top. The total number of times you took a shot, that goes in the bottom. You get a percentage. Okay, make sense? Okay. Another way is like with surveys and such. So here's an empirical probability. The company is conducting a randomly selected U.S. adults to determine how they read books during the past year. So far, 1,502 adults. And this is important. A lot of times when you have your questions, they will give you part of the answer in the question. What is our sample space? How much is in our sample space? 1,502. Now, we're going to see down here, you could get that same number by adding them all together, but you might save yourself some time because they've given us that. The pie chart shows the results. What is the probability that the next adult survey read only print books during this last year? So we come down here. Some people read no books, read print and digital, digital only. Here's the ones that read only print books. How many was that? 560. And again, it's this idea, if we randomly were to just choose someone from this group, what would be the probability of choosing one of these people? 560 out of what? 1,502. I think I've got it on the next page, so I'm not even going to bother calculating it. But yeah, see, they went and added them all up, but they've got the 1,502, which was given in the question. And then when you divide it, it's about a 37.3% chance that randomly. You also could say that 37% of those people read only print books. Okay. So we kind of do both of those. Make sense? So we can also do this. Remember, we started off making frequency distributions. So from a table, same thing. And again, a lot of times the difficulty is choosing the right numbers to use. We've got a company that's conducting a survey, randomly selected individuals to determine the ages of a social media application. So far, 3,000 users, and we can kind of see so that's the total of all frequencies, right? So that 3,000 is what to us? The population, the sample space that we're dealing with, okay? The frequency distribution shows the results. What is the probability that the next user surveyed is 25 to 34? So we focus on that group. How many are in this group? 675, 765, how did I say? I saw it, 765. And 3,000 is what it's out of. So that's the math. We take how many there are divided by the total sample space. And what do we get with that? 0.255, which is 25.5%. Remember, move the decimal over 2 places. So 3 different ways to write probability. And just when you're doing the homework, if they ask for a fraction, give them a fraction. If they ask for a percentage, give them a percentage. If they ask for a decimal, give them a decimal. If they don't ask for anything, then take a guess, right? Usually that means they want the fraction, but usually they will tell you, because sometimes they might say you're wrong, and it's not that you're necessarily wrong. It might be that you're just getting it in the wrong form, or the format that they didn't like. Okay? Doing okay. Law of large numbers. What's a large number? A million, a billion, a trillion. What this means is the larger number, the more times we try something, like flipping a coin, the more likely we are to get close to that theoretical probability. So here's an example here, flipping a penny, which I guess they're not going to be making those anymore pretty soon, right? Yeah. It cost them almost 4 cents to make a penny. It's only worth a penny, so I should have done this a long time ago, right?
4 cents to make 1 cent penny.
Yeah. Crazy, isn't it? Okay. Look at this. When we're below 30, we could, you flip the coin and you might be getting, see, almost like 75% heads. Or you get, so many percent tails. But you get out here to larger values, you're getting closer to 50%, which is what you kind of sort of expect. So that's just the law of large numbers. It doesn't apply to a single event. Okay? And this is sometimes called, if you go, like we've got casinos all around us, it's also called the gambler's ruin. The gambler's been gambling and he's been losing. He says, I've been losing so long, it's time for me to start winning. Not necessarily. So you bet real big and you still could lose. Or you're on a lucky streak and you think, today's my lucky day. Well, maybe just those first trials were your lucky day and after that are not. So probability doesn't have any memory. But the more times you do it, the closer you are to the average. Now, we haven't discussed it, but at a casino, who do you think has the greater probability of winning? The casino or the casino? That's why they're in business, right? And so the longer you play, the more likely they are going to be the winner. If you got lucky the first few times, what do? Take the money and run. Because the longer you stay, the percentages, the probabilities will turn it towards the house in any game. Okay. Maybe it's just, my friend just said, best to stay out of the casinos. Yeah. Now this is a third type of probability, right? We have classical probability, just divide. We had empirical, which is observed. And then subjective, well, this is what you feel. So here's one, a doctor says you've got a 90% chance of getting better. That's kind of subjective. Now, it may be from what his experience is, but it's still his opinion. Have you ever heard, if you get one opinion, go get another opinion? That's why you get that second opinion. Each doctor may have their own opinion, right? So that's a subjective probability. You're waiting at the coffee shop for your friend, and they haven't shown up yet. What's the chances they're going to show up? That's going to be subjective. Oh, I said something wrong to Jake. Maybe he's mad at me. Maybe he's not coming. So, subjective probability. So now, we're getting close, aren't we? Or
Yeah. 5 more minutes.
5 more minutes?
Till
5, 6, 7.
7 minutes. Okay, so let me finish this part, and then we'll get those out. What kind of probability is this? The probability that you'll get an A on your next test is 0.9%. What kind of probability? Classical, observed, or what was that last one? Subjective. Thank you. Is it subjective?
observe.
What do you think? And again, it depends. If you had been observing your grades, recording them, and then it was a 90% chance, you could say that it was observed. Okay, it was kind of, it didn't tell you, but most likely you're just feeling good. I studied hard, so I think I'm going to get an A. That's subjective. But if you every test you've taken, you've gotten around 90%, then that could be observed, right? Probably not likely it's going to be classical because you can't really do the math on it, but subjective. How about this one? Probability that a voter chosen at random will be younger than 35 years old is 0.3. Observed. Could it be? What do you think? What do they usually do at voting?
Surveys.
They do surveys, and so if they had a survey, this would be empirical or observed that that's what's been happening. 30% of them have been younger than 30 years old, 35 years old. Right, let me see. Oh, we got one simple one. I think I can do this without the slide. We'll pick it up at the end. If there is a 30% chance of rain today, what's the chance of not raining? 70%. So do you see how that works also, probabilities? We know the probability of something happening, probability of it not happening is the complement. Okay? Just subtract from one. We do it all the time, right? Oh, 30% chance, 70% chance of sunshine. Well, not quite sunshine, but not raining, okay? So I'm going to